Hi, this is John Whitaker, and this is our 27th video lecture for the Mathematical Analysis 2 class. And we're still talking about uniform convergence for a sequence of functions. And we've got some more facts here to prove. And here's the first theorem. It says, if f sub n is a sequence of continuous functions on E and f sub the sequence f sub n is n run from 1 to infinity converge uniformly to f, then f is continuous on E. And here, what we're doing is we're assuming E is some subset of X where X is a metric space. So what this theorem is saying, it's saying that if you have a sequence of continuous functions and they converge uniformly, what they converge to must be continuous. We saw examples of a pointwise convergence, and what it converged to wasn't continuous. So pointwise convergence of continuous functions, but what it converged to wasn't continuous. So that can't happen if we have uniform convergence. Okay, let's look at the proof. So, proof, we let f sub n be a sequence of continuous functions on E that converge uniformly to F. We want to show F is continuous on E. So we let X be some element of big E. So this X is like little x, not the big X is the metric space. Okay, and we want to show F is continuous at X. Okay. Now, this goes back to previous chapter, I believe chapter 4, where we had some information where we covered continuity functions. And what we'll do is we'll break this proof into two cases. So case 1 had to do with if X is not a limit point of E. And in this case, then F is automatically continuous at X. That was a result we had previously. Okay? So case 2, if x is a limit point, of E, okay? Suppose, let's say, x is a limit point of E. Okay, since f sub n is continuous on E, then the limit as t goes to x of f sub n of t equals to f sub n of x. And this is true for each n. Okay? That's with us having a limit point. Okay. So by the theorem we ended with last time, the limit as t goes to x of f of t equals to the limit as n goes to infinity of f sub n of x, which equals to f of x. And so by x being a limit point, we can show continuity by showing that the limit as t goes to x of f of t equals to f of x. So f is continuous at x. And therefore, since x was some arbitrary element of E, we can say, so f is continuous on E. And that's what we wanted to prove. So that is that theorem. The next theorem is a very important theorem. And so it says, suppose K is compact, and we're going to assume 3 more things. First thing is that the sequence of f sub n's is a sequence of continuous functions on K, so each f sub n is continuous on K. Second thing we're going to assume is that f sub n converges pointwise to a continuous function f on K. And then the last part that we're going to assume is that f sub n of x is going to be greater than f sub n plus 1 of x, and that's for all x element of K, and n being equal to 1, 2, 3, whatever. Okay. Here, that last assumption is telling us that we're saying that, so just as a comment here, so the f sub n of x are real value functions. Okay? Otherwise, we couldn't have that inequality. And then the conclusion the conclusion is that the f sub n's converge uniformly to f on k. Okay. All right, let's look at the proof. Well, we're going to start off by putting a new sequence of functions, g sub n, equal to f sub n minus f. Now, look, the f sub n and f are both continuous on k, so g sub n is continuous on k. As the difference between two continuous functions is continuous. All right, now note for each x in k, the limit as n goes to infinity of g sub n of x equals to the limit as n goes to infinity of f sub n of x minus f of x. And this is going to be equal to 0 as f sub n converges to f pointwise. Okay, so that tells us that the sequence of g sub n's converges pointwise, or converges to 0 pointwise. Okay. Now what we want to do, we want to prove, it would be sufficient to prove, that the g sub n's converge to zero uniformly. Okay, so here's what we use. We use the definition. We let epsilon be greater than 0 be given. We let k sub n be the set of all x's that are in k, such that g sub n of x is greater than or equal to epsilon. Okay? Now, if you look at the set y equal to the collection of all g sub n of x, such that g sub n of x is greater than or equal to epsilon, then these are output values that are bigger than or equal to epsilon. That's going to be, this is a closed set in R. Remember, the f sub n's were real value functions, so were the g sub n's. And so we're looking at a output value, so they're in R, and that's the set in R, and it's going to be closed. All right. Since g sub x is continuous, or g sub n sub x is continuous, then these k sub n's, they equal to g sub n inverse, the preimage, I should say, of this y. Okay. This is closed. Is closed. Okay. And the reason we get that is because the g sub n are continuous. So that's one factor we had earlier in chapter 4, I think. Okay. So since k sub n is a closed subset, of a compact set K, then that tells us that K sub n are compact, or is compact for each n. Now, since the g sub n's are going to be greater than or equal to g sub n plus 1, and that has to do with the definition of the f sub n's, then if quality of the f sub n's, property of the f sub n's, the same one, then if x is an element of k sub n plus 1, which is equal to the set of all x's in K, such that g sub n plus 1 of x is going to be bigger than or equal to this epsilon, then x is going to be an element of k sub n, which equals to the set of all x's in K, such that g sub n of x is going to be greater than or equal to epsilon. Yeah, so if g sub n plus 1 is bigger than epsilon of x, is bigger than epsilon, because of this inequality here, g sub n of x will be greater than or equal to epsilon, so x is in the k sub n. Okay. So what that tells us is that the k sub n plus 1 is a subset of k sub n. What we're going to do is we're going to fix an x element of k. Okay, since the g sub n's is a sequence, converge to 0 pointwise, we see that x is not an element of k sub n, not an element of k sub n, for large enough n. The k sub n's are equal to the collection of x's such that g sub n of x is greater than or equal to epsilon. But the g sub n of x's are going towards 0, so the g sub n of x's are getting closer and closer to 0, so we'll be within epsilon units eventually. Okay, so that's what we have. Thus, x is not an element of the intersection over all n's, natural numbers, of k sub n. So, this intersection of the k sub n's over all n's is empty. So we fix this x, it's not in there for any fixed x. It's not in this intersection, so this intersection must be empty. Thus, by previous theorem, and this is from analysis 1, and I'll write down what theorem it is. Because if the collection of k sub n's is a collection of compact subsets of a metric space, X, such that the intersection of every finite subcollection of the k sub n collection is non-empty, then n sub k of alpha. So I think I should have been writing alphas here, because it's any type of collection, not just of natural numbers. Let me go back here and make a correction. This, in the theorem, is case of alphas here. Okay. Make that change. Okay. So this is non-empty. This was a previous theorem. Okay. But this guy is empty. And so what that means that there's this case of big N is empty for some big N is a natural number. Okay? That's what we have. Okay, thus, for all n bigger than or equal to this big N, 0 is less than or equal to g sub n of x, which is less than epsilon. And that's true for all x element of k. And that tells us that the g sub n's of x converge uniformly to 0 on K. That was enough to prove the theorem. Okay. Next, we want to look at a definition. It says if X is a metric space, the script C of X will denote the set of all complex valued continuous functions, continuous bounded functions with domain X. So this is really a notation. So what we mean by this script C of X is the set of all complex valued continuous bounded functions to act on X. Another definition associated with this space is for each F in this space, in Cx, the supremum norm of F is denoted by double bar F and given by double bar of F equals to the supremum over all little x in the big metric space X of the norm, well, here I'll say the norm of F of X, and this is the complex norm. As a fact, C of X with the metric on it being defined by this supremum norm, difference in function in the supremum norm, is a metric space. That is, this D sub script C of X between G and F, given by the supremum norm between the difference between G and F, is a metric on C of X. And the proof of this fact, to show that this is a metric, the proof is going to be left to the students. That's something you'll have in your homework. Okay, a theorem is a sequence f sub n converges to f with respect to the supremum norm on C of x, if and only if f sub n's converge uniformly to f on x. In this theorem, the f sub n's converging to f in C of x, the f sub n's are thought of as points. They're functions, but they're like points in this space. And this is what they're converging to, f. Okay? Okay. So we want to prove this. So let's let f sub n, this is a sequence, okay, be a sequence in C of x. All right. So it's an if and only if statement, so let's go to forward direction. Let's suppose that f sub n's converge to some point, we're going to call it f, in C of x, okay, with respect to the supremum norm. We want to show f sub n converge uniformly to f on x. Okay. All right, so we're going to do this using the definition. Let, well, maybe not necessarily the definition, but we let epsilon be greater than 0 be given. Let's see how it goes. Okay, we need a natural number, script n, such that for all n bigger than or equal to this script n, then the f sub n of x minus f of x will be less than or equal to epsilon. And that's true for all epsilon of big X. That's the definition. So we're using the definition for uniform convergence. Okay. Okay, well, since the f sub n converge to f and c, of x, then there exists a natural number such that, let's call it a natural number n, such that for all n bigger than or equal to this big N, this metric, here it is this, f sub n minus f double bar, will be less than epsilon. So for all n bigger than or equal to this big N, the supremum of all x's in big X, space here, of f sub n minus f, write down f sub n of x, minus f of x, and the norm on the complex numbers is going to be less than epsilon. Thus, for all n bigger than or equal to big N, the f sub n of x minus f of x in the complex norm will be less than or equal to epsilon. And that's what it takes. Thus, that's what it takes for the f sub n to converge uniformly to f, and here I'll say on x. Okay, so that's half the proof. Okay. Okay, going in the other direction. Suppose the f sub n's converge uniformly to f on x. We want to show the sequence of points f sub n converge to f in c of x. Okay, so we let epsilon be greater than 0 be given. We need a natural number n such that for all n bigger than or equal to this big N, the f sub n minus f and the supremum norm will be less than epsilon. So since the sequence of f sub n's converge uniformly to f on x, well then there's going to exist a natural number. So there exists a natural number, call it big N, such that for all n bigger than or equal to this big N, f sub n of x minus f of x and the complex norm will be less than or equal to epsilon over 2. And that's true for all x element of x, big X. Thus, for all n bigger than or equal to big N, the supremum over all x's in big X of this norm will be less than epsilon. So that says for all n bigger than or equal to big N, this supremum norm between f sub n and f will be less than epsilon. And that's what it takes for the sequence of points f sub n to converge to f in C of x. So that ends that proof. The last theorem we'll do today states that this C of x with the supremum norm is a complete metric space. Now, what a complete metric space is a metric space such that all Cauchy sequences converge. Let me write that down. Okay, that's what's happening in C sub x. Every Cauchy sequence converges. All right, let's get the proof done here. Proof. We let f sub n be a sequence of points. Not only a sequence, but be a Cauchy sequence. And C of x. Okay. We let epsilon be greater than 0 be given. Okay. Thus, there exists a natural number, script n, such that for all m and n, I think I know I'm right now, n and m, bigger than or equal to big N, the supremum norm of f sub n minus f sub m will be less than epsilon. Thus, for all n and m bigger than or equal to this big N, that's what it meant to be a Cauchy sequence, the supremum over all x in the space, big X, the complex norm of f sub n of x minus f sub m of x, that's going to be less than epsilon. Thus, for all n and m bigger than or equal to this big N, f sub n of x minus f sub m of x will be less than epsilon. And I'll say less than or equal to it. It's less than or equal to. And that's true for all x element of big X. So, by the Cauchy criterion for uniform convergence, f sub n converges uniformly to some function f on big X. Okay, so note by a previous theorem, since the f sub n's are continuous, how do I know they're continuous? Well, they're in C of X. That's what each one's in C of X. That's what it means. Part of what it means to be C of X, that you're continuous on X. Then, and we have this uniform convergence, then F is continuous on X. What I'm trying to show is that F is an element of C of X. So it's got to be continuous, it's got to be bounded, a complex value function. Right now we've proven that F is continuous. Since F is uniformly, since the F sub n's converge, uniformly to F, there exists a natural number n sub 1 such that for all, the complex norm of f sub n of x minus f of x will be less than or equal to 1, and that's true for all x element of big X. Thus, this is the complex norm. Okay, so sometimes I might omit that, but remember this is the output values for these functions, which are complex value functions. Thus, the absolute value of the f sub n sub 1 minus the norm here of f sub n, these are of x here. This is just f, not f sub n. Is going to be less than or equal to 1. And that's true for all x element of big X. That's because this guy right here is less than this guy. Thus, what we get is that minus 1 is less than or equal to the f sub n sub 1 of of x minus the f of x in the complex norm, which is less than or equal to 1. Okay? And that's true for all x in big X. So what this is minus 1 minus f sub big N sub 1 of x will be less than or equal to minus the norm of f of x. It's going to be less than or equal to 1 minus the norm of f sub n sub 1 of x. And that's true. This is a 1 here. Let me make the 1 a little bit fancier. And that's true for all little x element of big X. Okay. So that says multiplying both sides of that inequality by minus 1. We have hold on just a second. So what I can say is that minus 1 minus f sub n sub 1 of x is going to be less than or equal to minus the norm of f of x, which is going to be less than or equal to 1 plus the norm of f sub n of x. And that's true for all x element of big X. So all I did was change that minus here to a plus, so I got something bigger. And so that says that minus 1 minus the norm of f sub n of x is going to be less than, I'm multiplying everything by minus 1 and switching the directions of the inequality. Norm of f of x, which will be less than or equal to 1 plus f sub n sub 1, should be n sub 1, of x, so this should be n sub 1. Okay, and so that what that tells us is, so the f, or I should say this, since f sub n sub 1 of x, without the norm, is bounded. How do I know it's bounded? Well, it's in the C of x. So it's bounded. There exists an m greater than 0 such that the norm of f sub n of 1 of x is less than or equal to m, and that's true for all x element of big X. So what we have is the f of x in norm is going to be less than or equal to 1 plus m, and that's true for all x element of x. So f is bounded on x. Almost done. Thus, we have f converges uniformly. I'm sorry. Thus, f is an element of C of x because it's a complex value function, it's continuous, and it's bounded. And since f sub n's converges to f uniformly, on X, then that tells us that F sub n converges to F in C of X points. And that's the proof of this theorem, and that ends the lecture for today.